Okay, this is a video recording of Lesson 6 titled Object Composition, Static Structures, and Object-Oriented Pillars. And these three topics are not necessarily connected or inherently related, but we're just going to kind of throw all three of them together in this lesson just for the sake of timing. Okay, so we're still here in the course, although I was thinking more about this diagram and felt that it wasn't really reflective of all the complexities and language features we've been talking about with C#. So we're kind of writing off all the stuff we've been talking about in the previous lesson and what we'll talk about in this lesson with just this generic C# icon in the stuck in the corner of this diagram. So hopefully, as the semester goes on, this diagram will get more interesting, and we'll start introducing new tools that our programmer will use. Okay. So first section here is about object composition. So object composition is the idea that objects can be composed of not only primitives, but also of other objects. So and we have seen this in homework 1. So if we review our student class from homework 1, we see that it has some primitive properties that it is organizing together. So first name, last name, jelly bean, house, they're all strings, they're all primitives. But it also has another object that it's being composed with, right? So it's using the datetime object to represent the birth date of a student. Okay, so we've seen this, and the difference between what we've done previously and what we'll do today is simply that datetime is an inbuilt C# object that is provided by the .NET application framework. We didn't have to define what a datetime was, but what we'll see today is that we can compose objects, we can create custom objects, and then also define the other objects that a given object is composed with. Okay, and so another kind of view of this is we can say that object composition is used to model a has-a relationship between objects. So a student has a birth date, a calculator has a list of buttons, right? A phone has a lock screen, right? So it's this has a relationship we're getting at with object composition. Okay, so let's see an example here on the trivial end here. So we have a dog class, so similar to the dog classes we've seen before, but now we can see that a dog also has a collar. Okay, now C# doesn't know what a collar is, so we also have to tell it that. So here we have a definition for what a collar is in general. And you can see color is also composed of another object called color. So your color object probably contains a value for red, an integer value for green, and an integer value for blue, and that's what makes up a color object, something like that. So so here we're combining we're combining the definition of a collar within the definition of a dog. And so now when we look to use our dog objects, we have a little more work to do. So you can create your dog, and you can set the simple property. So you can just say name equals Marley. But to set a collar on the dog, now you got to create another object to put in the holding spot for collar. So we create this collar object. We can set the color of the collar. We can set the tag that's on the collar. And then after we've created this collar and populated it with some information. And then we can say, well, my dog.collar is equal to this collar object I created right up here. So a little bit more work here to set the collar property on a dog, but if you can see it allows us to structure our information in a useful way here. So, because if we didn't do this, then we'd have to start, on our dog class, we'd have to write, collar color of type color and collar tag of type string. So we'd have to like prefix everything with collar, but we can just put that in the definition of a collar. Okay, so that's on the simple end. This is also on the simple end, kind of an example that's getting at it in a little bit different way. So here we have a vaccination, a private field called vaccinations on our dog class. It's of type list of vaccination, and we initialize a list in the constructor. And here you can see we have this administer vaccine method in the dog class, and that takes in the name of the vaccine we're about to administer. But here you see in the definition of a dog class, we're also providing the instructions for creating a vaccine. Okay, so or for adding a vaccine to a dog. So we just take in this primitive value, vaccine name, and within this method we create the new vaccination object, and we set its properties. So we use the vaccine name for name, and then we use datetime.now for the injection date, and then we can add it to our list. Okay, so and here you can see how it looks when you go to use this. You just do marley.administer vaccine, pass in your string and the instructions for building the object and storing this information under the hood for the dog is all defined here in the class. Okay. So a slightly more interesting example here is this drone controller class. So we have some private fields for an up-down stick on a drone controller and a side-to-side stick on a drone controller. And then we also have the drone that the controller is controlling. Okay, so we have these other objects that are in the definition for a drone controller, and we can use those other objects within this drone controller to do some work for us. Okay, so if your user's holding the drone controller, and they push the left stick either in a positive or negative direction, you can use this joystick object to do some work. So translating the amount the stick was pushed by into the velocity change in the propeller of the drone, right? So we're using this other object in the implementation of this method here. Okay, and then we can update our drone, right? This is the object we're controlling. Okay, so same thing with the right stick. We can use these underlying objects to do some work for us. And the has-a principle still applies here too. So a drone controller has an up-down stick, it has a side-to-side stick, and it also has a drone that it's controlling. And here we're able to compose a drone controller out of these other objects. Okay, so now we move on to static versus non-static. And to be clear, this is different than the conversation we had about static typing or statically typed languages and dynamically typed languages. This is different than that. Static is this keyword or language feature that pops up in C#, and so we can see examples of that here. So public static class, public static double, right? So it's this keyword that pops up. Now, when something is marked as static, that means in our worldview, our program's worldview, there is only one of those things. Okay, just one single version of that thing. Okay, so this is opposed to, for example, student objects or thermostat objects or drone controllers, right? There's multiple of these things in the world. There's multiple students, for example, in homework 1, there's multiple thermostats, and so on. So there's multiple of those things, but sometimes there's only one. And things there's only one of are marked static typically. Okay, so an example of that is for example, the math class, right? So this is inbuilt into C#, but you can kind of peek at its definition and you'll see, well, there's only one value for the constant E or for pi, right? There's only one of these things in the world, and so it's a natural. It's natural for that to be considered static, okay? And for example, absolute value is another example of that, right? There's only one function that exists in the world, or that's needed in the world to take the absolute value of, for example, an integer, right? So only one formula for doing that. Okay. Datetime.parse, that's another, we've used that one. There's only one algorithm in our C# program for taking a string and converting it to a datetime object. I mean, we could write more of our own ones, but that the one that comes with datetime objects, there's only one of, right? So that's datetime.parse. Math.round, same example. Okay, so what this means is when we want to talk about things that are static, we're not using the new keyword. So new keyword is used for creating new instances of objects, right? New students, new thermostats. But when we're talking about something that's static, or when we want to refer to something that's static, we just use, for example, the class name and then the property name. So math.round, datetime.parse. There is no new involved here. Because we don't need to create new things. Well, we just want to refer to the single existing one in the program. Okay, so that's intro to static here. Let's look at another example here. So this is from the previous lesson exercise. I provided these user input helpers, and I gave them in the form of a static class. So public static class user input helpers, and it has these helper methods that are that you can refer to just by going user input helpers dot prompt for string, prompt for double, and so on. So you'll see the static keyword is embedded in here between the access modifier and the return type. We have static, and the idea of this being, we only need one algorithm or piece of code or function that describes how to get a piece of information from the user via the console, right? And while we're looking at this, console.readline, also another static method, right? So, all right, let's look at a slightly more involved example. So the other thing too is you can combine static and non-static components within the same class, right? So here we have a public class rabies vaccine, and you can create rabies vaccines, right? You can create a lot of these and administer them to animals, but there's also some things that are just globally true about rabies vaccines, right? So there's a recommended first dose in milligram. These numbers are made up. I don't know if they're accurate or not. There's a recommended quantity to put in the first dose of a rabies vaccine, and a recommended quantity to put in the second dose of a rabies vaccine. And there should be a recommended spread between when you administer the first shot and then the booster shot. Okay, so these components are globally true about all rabies vaccines. But now we can also create individual rabies vaccines to administer, and the definition for those is down here. And so none of these are marked as static. These represent how an individual rabies vaccine works in general. Okay. So let's see that in use. So here we have the dog class, right? Of course, there's many dogs, and dogs have multiple rabies shots. And when we administer a rabies shot, we can perform some logic on the dog on this administered vaccine. Seeing, is this a first shot? Is this a second shot? And while we're doing that, we can also refer to the static properties about rabies vaccines. So when we create a new rabies vaccine, we can set the dosage to the recommended first dose, and then whatever the time is, we use that as the injection date. All right, so let's look at this constructor real quick. So rabies vaccine takes in a dose in milligrams, and if we look here, well, what's the dose of milligrams where this rabies vaccine is taken in? Well, it's the globally established recommended dose. Okay. And then in the second case, we can refer to if they already had a rabies shot, then we can make sure that we're not injecting it too soon. So we can check we can refer to the globally established recommended spread between doses, right? So we're referring to this value here, spread between doses and days, and we can use that in our logic for administering a single vaccine. Okay, and then create the new vaccine, and then use the recommended second dose, and then the injection date. So otherwise, we don't administer the shot. So you can see here we're writing instructions that are going to operate on a single dog, but we also refer to these kind of global properties to inform, this function here, this process of administering. Okay, last section of lesson 6, we're going to talk about the object-oriented pillars. So the 4 object-oriented pillars are abstraction, polymorphism, inheritance, and encapsulation. And these are ideas or concepts that kind of drive how we want to design object-oriented programs. So we're going to talk about what these concepts are, what ideas are they referring to, and then how do we use C# to implement these ideas in our code. So if you like acronyms, there's an acronym for these 4 pillars here, API here, abstraction, polymorphism, inheritance, and encapsulation. And there may be more pillars, but we're just going to talk about these 4 here. Okay, so we'll start with encapsulation. Okay, so an example of the idea of encapsulation is here. So when I think about cars, I think about them very superficially. I think about what color are they? How do they look? What year are they? How many miles do they get per gallon, right? So I think about these superficial attributes of a car. And what I never think about is this. All of this junk under the hood, cast aluminum shock towers, heat pump climate control system, heat exchangers, right? I don't think about these things when I think about a car. And the reason I don't have to think about these things is because all these complex internal components of a car are tucked away and hidden away. So I can be superficial in my thinking of cars. Okay, all the complexity is hidden there under the hood, and I have no business opening that hood unless I'm a mechanic or I'm interested in those internal components. Okay, so the key idea, right? Hide complexity from the common user. And we really love this as programmers. Okay, we love it when complex stuff is tucked away and the code we have to write is simple. So a programming example is, if you think back to the lesson 1 exercise, we use the random object to generate a random number between 1 and the size of a dice. And I'm sure that random object has a big, beautiful algorithm for generating these random numbers, but I don't really care about that big, beautiful algorithm. I just want to go, my random object dot get random integer, right? And that gives me a random integer that I can use for what I want to do. So random object encapsulates all that complexity that's involved with generating a random number and makes it easy for me to get random numbers. Okay. So let's go back to the car example. So saying what we said about cars in C#, might look something like this. So we use these private fields to hide these complex internal components of a car, right? Your power steering system, your internal braking system, safety response system. You hide all these things in private fields so that whoever's using the car class doesn't have to think about these components of a car. They are empowered with the opportunity to be superficial, right? So they can just think about what's the make, what's the model, what's the color. So this is what we show, but this is what exists, but we hide that it exists. Okay, so that's our general strategy for encapsulating things. Okay, so the next idea here is abstraction, and this is closely related to encapsulation. And the idea of abstraction, at least in this sense, is we want to provide users with an interface that gives them access to essential features of an object or essential functionality of an object while hiding all the underlying complicated implementation details. Okay, so that's the idea of abstraction. And if we go back to cars, right, what's our abstraction? This is our abstraction. Okay, so how does a user interact with a car? They have a steering wheel, and they have a brake pedal, and they have a gas pedal, right? And that's really all they need to understand, is that you turn the steering wheel, the car turns, you brake, the car decelerates. If you press the gas pedal, the car accelerates. So this is our abstraction, and this gives us the interface for interacting with the car without thinking about the underlying complicated details. Okay, so to say that, but in C#, we still have our public class car, and here's our interface to interact with the car, interact with the core functionality of the car. So we have the public void turn steering wheel method. This allows us to turn the car. With some validation, we can only go so far to the right, we can only go so far to the left. So we have this interface for accelerating, so we press gas pedal and we press brake, but under the hood, the car needs to leverage these other systems, these other subcomponents of it. So when we turn the steering wheel, we have to engage the steering system and turn front wheels, right? When we press the gas pedal, we have to talk to the drivetrain system and accelerate. When we press the brake pedal, we want to talk to this brake system that is going to activate these brake pads that push against the rim of our steering wheel to slow it down, right? So this is what we see, but underneath there's these different systems interacting. Okay, so our abstraction is for the functionality of a car is these three methods, right? The three methods we marked as public. Okay. Next idea here is inheritance. So the idea of inheritance is that similar objects can be organized in a hierarchy to share properties and behaviors between them. So a classic example of this is, for example, at Hogwarts, we represented students, but what if our program also needed to represent professors? And so students and professors have a lot of things in common. So how do we say, these things have a lot of things in common without having to duplicate code? So here's a Venn diagram of saying that, right? So students and professors, they have all these things in common: first names, last names, birth dates, jelly beans, but they also have things that are unique to them. So students have student IDs, whereas professors have employee IDs. Students have a house they get sorted into. Professors have office hours, right? Students have class schedule. Professors have classes taught. So there is, this is essentially, it's just a Venn diagram, right? We're saying some things have things in common and also some unique components to them. So let's organize that Venn diagram into a hierarchy instead. So if we think about it in terms of a hierarchy, a wizard, all wizards have these four things. All wizards have first names, last names, birth dates, and jelly beans. Now, a student wizard also has these additional properties. So a student has everything a wizard has, plus a house, a class schedule, and a student ID. And professors have everything a wizard has, plus classes taught, office hours, and employee ID. So this is when we think about an inheritance hierarchy, we think about it like this. Okay, so now we say that in C#, right? And we still have our hierarchy, except we have this public class wizard. Okay, public class wizard. It has those four properties, and additionally, there's a method for casting a spell. Okay, and a student class inherits from the wizard class. So if you see the syntax here, student : wizard, we are saying that the student class is everything the wizard class is, plus this additional stuff. Okay, so it's those same three properties, and additionally, our assigned a house method is in here. And professor is the same thing. So a professor : wizard says a professor is everything a wizard is, plus these additional properties. And then additionally, they have a method for awarding house points. Commonalities are kept in the parent class, we might call it, and unique items unique components are kept in these child classes that inherit from the parent class. Okay. Last pillar here, polymorphism. So we covered them in these pillars in this order because to understand polymorphism, we had to understand these other pillars as well. But the general idea of polymorphism is that objects that have the same abstractions can be used interchangeably regardless of their underlying implementation. So that's the key idea of polymorphism. And so in the physical world, what's an example of that, right? So back to cars here. If you think about these three different cars, one of them is, I think this is a Honda Civic. This is a combustion engine car. And the middle one here is a Tesla, so this is our electric car. And the one on the right here is a Prius, so this is our hybrid car. It uses an internal combustion engine, but it also uses an electric battery and drivetrain. So these three cars all work very differently under the hood. Their implementation is different, but they all share that same abstraction of a steering wheel, a gas pedal, and a brake pedal. And so when we think about polymorphism, we say, well, because they share the same abstraction, we can use any of these cars interchangeably. So even if I drive a Honda Civic, I can hop in a Tesla and I know how to use it. Okay, it's because it has that same abstraction. Okay, so let's start talking about this in terms of C#. So we want to define our abstraction more concretely here. So we use this class car, so public class car, but now we have a new keyword, abstract, public abstract class car. And what we're saying is no one ever just creates a car. They create a combustion engine car, or a Honda Civic, for example, or they create an electric car, a Tesla, for example, or they create a Prius, right? But no one just creates this car. A car is an abstract thing. It's not specific. It's not exact. But we use abstract classes here to describe the common abstraction. So the common abstraction is turning steering wheels, pressing brakes, and pressing accelerators. Okay. So here we can inherit from that abstraction. So we can say a Honda Civic is everything a car is, or in this case, a Honda Civic has the abstraction of a car. And by the way, this is how it works internally. So, it has a combustion engine, and when you press the accelerator, for example, you engage the engine, you burn gasoline, and you burn that gasoline in the engine to generate power, and then you use that power to accelerate a drivetrain. Right? This is a simplification. I don't really know how cars work, but you get the idea. We are saying if our car is a Honda Civic, this is how we implement the abstraction of pushing a gas pedal. These are the instructions for doing that. Okay. And so if we look at the Tesla abides by a Tesla is a car. It abides by the abstraction of a car, but when we press the accelerator, we have some slightly different instructions. So we draw electricity from a battery to generate power, and then we use that power to accelerate a drivetrain. So the instructions are different, but we still have a public method called press accelerator, and the reason we have a method called that is because our abstraction here, public abstract void press accelerator, is defined in the parent class. Okay. So that's the Tesla, and then the Prius, right? As you can imagine, is just another implementation of, well, if the car at hand happens to be a Prius, what are the instructions for to execute when you press the accelerator? And you do a hybrid of things, right? You pull some power from the battery, you pull some power from the engine, and you accelerate a drivetrain, right? Of course, probably an inaccurate simplification of how these different cars work, but you get the idea. the cars can work differently, but because they share the same abstraction, we can do things like this in our programming. So here we have a program, and the program creates a list of cars, right? So generically speaking, all these things are cars, right? So it's a list of type car. But specifically speaking, what are the cars in this list? We have a Honda Civic, we have a Tesla, we have a Prius, and we create this list, and when we create this list, we can now do things that you can do with all cars. So, we have a for each loop, and we're looping through every car. Even though all the cars are different, we can still execute the same instructions here. Press the accelerator, turn the steering wheel, press the brake, turn the steering wheel, press the accelerator, right? Because we have this abstraction defined, right? This is where we define the abstraction. We can use the different types of cars interchangeably in our program. Okay, that's it.